Coming to you live from my kitchen. Hi, this is Dr. C, and this is the first of many screencasts that I'll be doing on the different topics we're going to be covering in biology. This is related to the reading that you just were assigned, so now we're going to do a review of atoms, isotopes, ions, and molecules. So let's take it away. First of all, you remember from your chemistry days that everything we know of really can be sort of broken into two big groups. One is that everything is either matter, or we could also then talk about energy. So matter and energy is what we're really going to be talking a lot about in this section. So life is composed of all those things that we call matter. And for matter, we think of it as stuff, right? Things that we can actually see. It's tangible. We look at the periodic table. But by definition, matter, it has to occupy some space and has to have some mass. So we're going to look at the elements, which are unique and pure forms of matter. And then we're going to talk about how those combine to ultimately form some of the compounds we're interested in. So let's get started. So elements are the simplest substances. In other words, when we call something pure, what we mean is that if we looked at it from the atomic level, what we'd see is if we took a bunch of sodium, for example, and we took out the atoms individually and we looked at them, they would all be the same, almost the same. So there's a little bit of a caveat there, but almost all of them would be identical. But one thing we know is that we have this beautiful tool, the periodic table, that organizes all the known matter, or all the known elements which make up matter on our planet. And each of those elements has a symbol. So S equals sulfur, and Ca equals calcium. And these are two that are important in biology, by the way, as well as these four elements: carbon, oxygen, hydrogen, and nitrogen. Now, I often kind of reverse these two. These oxygen and nitrogen, only because I call it Chon, C-H-O-N, is just something I use in class. So when you hear me say Chon, what I'm talking about is the element carbon, hydrogen, oxygen, and nitrogen, just FYI. So here we can see the ones that why we care about these elements in particular is because they form so much of the living world. They form a lot of us, and they form things in our atmosphere and the Earth's crust. So what you see here is just the percentage of each of these four elements in human beings. So you can see we're largely oxygen, and then we have carbon, obviously, because carbon is a very important element that we use to identify things which have an organic origin. And we have hydrogen and nitrogen. So you can see what that percentage is. Interestingly, look at the atmosphere next to it, and you see that really most of the atmosphere, the air around us, is made of nitrogen, and a little bit of these two maybe, and then the rest of it is made up of oxygen. And then the Earth's crust has a tremendous amount of oxygen too. And when we say that, usually we're saying that those elements, that oxygen, for example, is not generally in free form down there, but it may be combined in some type of a compound. So that's where we do find quite a bit in the Earth's crust. So an atom, just to refresh our memories, is this very small thing. We've used some symbols to show it. Smallest unit of matter that retains all of the chemical properties of an element. So if you break an atom down into its parts, which would be the protons, the positive charged particles, neutrons, which don't have a charge on them, and both of those are found in the center of the atom, which in this case we call a nucleus. And then the outermost region are the electrons, which have a negative charge, and they're held in this orbit around the nucleus. So there's kind of an interesting tension that goes on where we have these positive charges with the neutrons neutral all sort of packed in the center of this atom, and then the electrons, which are being held in very particular regions outside the nucleus. These are all referred to as subatomic particles, meaning they're not atoms, but they make up the atom. Here's the charges, and you can see what those are, and the areas located where the electrons are located are called orbitals. But when you look at the charges, so you have a positively charged proton and a negatively charged electron, and those two, if you think about it as a whole, would have a net charge of 0. So in the average atom or of an element on the periodic table, the proton number and the electron number are the same. They're equivalent, so the charges cancel. We'll see that. So here's a picture. This is helium. You may recognize that it has 2 protons here, and it's the proton number that identifies what element it is. So if you know the proton number, it's like its identity card for the element. You know what element it is. So every atom that has 2 protons, if you went out there hunting for them, they would all be helium. If we were able to throw another proton in here, it would no longer be helium. And some of you are automatically going, oh yeah, because that would be another element we know of called lithium. But also notice here we have these 2 protons, we have 2 neutrons with no charge, and then we have these electrons. And they are found in a particular location orbiting around this nucleus. They don't get closer, they don't get farther, they just stay sort of within this range. Okay, and that's a concept that we'll talk about a little more. So the atomic number is actually what we call the number of protons. So whatever the number of protons is that element's atomic number. The atomic mass is whatever is in the center where that nucleus is. So that's roughly this sum total of the protons and the neutrons in that particular atom of that element. Some of the elements may have a little bit different mass number depending on whether or not they have a few more neutrons or fewer neutrons. And so when you look at an element that has the same proton number, because it has to, it's that element, but it has a different number of neutrons, we call that an isotope. So we'll take a look at this coming up too. I'll do this in class a little more. Electrons aren't really counted when we find the mass because they're so small that they really don't add up to enough to make them useful in this. So when we measure the mass of an atom, basically it's what the protons and the neutrons are combined. Atomic mass is called the AMU. And I'm going to see if I can move me away a little bit just so I'm not in the way. There you go. Sorry, kind of off to the side. So when we try to figure out, if we had the atomic mass, we could figure out how many neutrons we had if we knew what element it was by just subtracting the atomic number from the atomic mass. So here you can see what you see on the table. This is just one depiction of it. Some tables look a little different, but basically the symbol is found by letter. It's a 1 or 2 letter symbol. The first letter, if there are 2, is always capitalized, and if there's a second one, it's always in lowercase. Here's the atomic number, protons. Here's the atomic mass, which is the sum total of protons and the neutrons. Notice that on this one, carbon could also be called, we could call this carbon 12. And you can see they've written it down here. And that this one up here would be called carbon, because it is carbon. It still has 6 protons, but is carbon 13. So that's how we read these. So we mentioned that an isotope is the form of some element that has a different mass because it has additional neutrons in it. So the very lightest element of all, as you all probably remember, is hydrogen. And normally when we look at hydrogen, many hydrogens have nothing in them but a proton. So here's, and with hydrogen we actually have different names that we call it. But we don't need to worry too much about this. Here we can see, though, in this case, this hydrogen actually has a neutron, and so it's called deuterium, and it has a little bit more mass. And here's tritium, which has an additional one. So these are all isotopes of hydrogen. Now, in your book, you can follow this. Some of you have used this website from University of Colorado called PhET in your physics classes, and hopefully you went on and did this simulation. So I can't do that here, but we will talk a little bit about it if you have questions.